right? So, waves by our Purnanandam sir, Dr. M. Purnanandam sir. And also, I invite our Dean Madam and HOD, our Department of Physics. Okay. So, now I invite our Dr. M. Purnanandam Garu. Come on the dais and occupy your seat, sir. Then I invite our Dean Madam and HOD of Department of Physics. Madam, come and take your seat, Madam. So now I hand over this lecture program to our HOD, ma'am. Thank you.
Thank you, Usha. A very good morning to all of you. Yeah, I once again welcome you all for this lecture program today. We are going to have a lecture on waves and oscillations by Dr. Purnanandam Garu. Right? At the outset, I would like to thank Dr. Purnanandam sir for accepting our invitation to deliver a lecture today for all of you. This lecture on waves and oscillation is a part of your syllabus, which you are going to have your practical sessions also. You are going to do the practicals also related to waves and oscillations. So these waves and oscillation is a very, very important topic for particularly science in general, and particularly for the students of physics as well as the engineering students also. Because you come across many aspects in waves and oscillations. For example, if you take optics, you study light. You know light has a dual nature, right? Wave nature and particle nature. The similar way, if you study electrical and electronics, you know the signals, how the signals will move like a wave, right? So in all aspects, we find waves and oscillations. In a way, they both are interrelated to each other. Because oscillation is nothing but a periodic movement of a system or a particle, right? Waves are created by the oscillations. So there is a relation between waves and oscillations, and Dr. Purnanandam Garu is going to discuss about what are the waves and what types of waves are there, what are the oscillations, and what is simple harmonic motion, what is damped harmonic motion, and we know free vibrations, forced vibrations. So all these things sir is going to discuss with you regarding the oscillations and regarding the waves also. We have what is the definition of wave, and what is the nature of the wave, and also how many types of waves, like standing waves are there, transverse waves are there, how in which media, how the waves are propagating. So all these things Dr. Purnanandam Garu is going to discuss about you. So let me tell you very briefly about Dr. Purnanandam sir. Sir is very closely associated with the Department of Physics since 20 years. I think he has contributed a lot when we are developing our post-graduation labs particularly, and in all aspects we are going to revision, and when we are going to have our material writing. So he's also the course writer, he's also the course editor, and he has done so many video lessons, audio lessons. And sir has participated in teleconferences of Dr. BRAOU. So in a way, he is like our faculty member in the Department of Physics. So whenever we have any type of problem, or whenever we need anything like expertise, we used to call Professor Dr. Purnanandam Garu, and he is very much ready whenever we call him to come to the department and assist the students and clarify their doubts regarding the subject matter, regarding the practicals and everything. So thank you very much once again for having come to Department of Physics and deliver a lecture on waves and oscillations. Students, this lecture, with his rich experience, he is going to teach not only lecture, he's not only giving the lecture, he's also demonstrating some of the things which he is going to teach. He is going to lecture in the topic today. You please concentrate on the subject, and he's very much he has a rich experience, so you can ask your doubts and clarify your doubts also regarding the practical as well as the theory part also, because we're going to have the practicals also regarding waves and oscillations, right? So be careful and be attentive in the class and listen to Dr. Puranandam Garu. Thank you. Thank you once again, sir.
Good morning, ladies and gentlemen. You are all very well grown up. I can't call you students. You are as big as 30, 40 years and other things. So very nice that I have been given an opportunity. Professor Madam has exaggerated many things. I am only a counselor. Of course, it was right from 1984 when the university started. I went on doing the counseling work. So a counselor will do teaching also. So like that, it is something like a homecoming for me to this lab, this department. They have affectionately called me. I'm thankful to them. I'm also thankful to all of you. Here, we will start with a primary school. In a primary school, usually the teacher teaches, makes the students to shout. 2 ones are 2. Everybody will say 2 ones are 2. So once we will try. Come on. Have you heard? Is it a superposition of all the waves that are heard by you? Is it not? If everybody's voice has the same frequency, you will have a single wave. And single wave coming from one person and such waves coming from different persons, they are all superposed. So once when they are superposed, you will have the amplitude of the wave is getting increased. But each one of you have got your uniqueness of the voice. So hence what will happen? Frequency is not matching. And some of you are shy, you don't shout. You felt diffident. So volume also is lesser. So what type of wave you can expect? It's a very complex wave. If you have something like this stand and a pendulum bob, many of you must have, are you able to see? If you pull like that, it will be oscillating. Okay. Now in the same way, if you apply certain load to this, it will be oscillating. It will be producing oscillations. What is the difference here? You have a thread is tied there, and you will have a heavy bob. This is oscillating. Suppose I leave like that, will it continue oscillating like that forever? Why? So there is friction. Whenever you have friction, what will happen if there is a friction? Loss of energy. So loss of energy means it cannot go to the same level. It has to reduce its amplitude. After, say, for example, 10 minutes, it will come to nearly equilibrium position, stand still. Now, same thing will happen wherever you have the oscillation. But when Earth is going around the sun or moon is going around the earth, what is the amount of friction? Can you have a friction? Imagine that there is a friction. What will happen? When Earth is going around the sun or going around itself, if there is a friction, what will happen?
After some time, you will come to the.
We will not have our sunrise, sunset, all these things. It will be a very collapsing situation. We cannot imagine that life. So our Earth is going around itself in an excellently, absolutely frictionless way. So you find, are you finding same time it is giving sunrise? Yes or no?
No.
Definitely no. All of you? The others are not speaking. So the no is correct. Why is it not like that? What is the reason?
Tilted by some kind.
When it is tilted, automatically the position of the sunrise of today is different from tomorrow, is different from the next day. Like that, it will be going on. Because of the tilt, there is an additional wave movement. What is that additional wave? That is called precession. Have you ever observed that the axis of the Earth is going around another axis? Have you imagined that? So we are transgressing from our waves and oscillations into rotational dynamics. So all these are interconnected. For convenience, divide our syllabus into parts. So that part is the rotational dynamics. So here, the rotation is or a circular motion or a repetitive periodic motion. All these things, they produce wave. Now, how many types of waves are there? Can anybody say? What are they? Here, you require to know one more thing. Are we talking about sound waves only or material waves only? So there are two types of waves again. One is material wave. Another one is, what is the other one? Material wave is sound wave. Other one? Mechanical wave is sound wave. Other one? Electromagnetic wave. So we have electromagnetic wave. We have material wave. Material is associated with some material. For example, this is a material wave. Are you able to see? Yeah. This is material wave. This is also a material wave. Electromagnetic wave. Can you give an example of electromagnetic wave?
Frequency in supply frequency.
Why are you so much thinking? You are able to see me. How are you able to see me? Light. Visible light is electromagnetic wave. So like that, you have electromagnetic radiation also is a wave phenomenon. So electromagnetic or material, a wave phenomenon. What are the various properties of, say, for example, it will be simple for you. Light is an electromagnetic wave. What are the properties of light? It is progressive. It moves from one place to other place. You switch on the torch, the light will go. Or a candle, the light will go to whoever that is seen. Okay. Then other property. Huh? Property of that light wave. Property of the light wave. It can be reflected. Is it not? So it is, reflection is a property of light wave. So whatever is the property of wave, whether it is electromagnetic or it is a material wave. So both means both will have their properties available in both the things. So a material wave is transmitted, a material wave is reflected. Okay. So other than reflection, what is there? We have refraction. Material wave is also refracted. Okay. If I am speaking from here, somebody listens my voice beyond the wall. So it is refraction. Right? So other than refraction, what else is there? What is the other property? Light property. You have studied all these things, no? Yeah, talk to me, not your friend. Property. There is what is called interference. You have studied that in your intermediate. Okay. One light wave, another light wave, they interfere and produce interference effects. Similarly, a sound wave also is having interference. You can show interference like a chill wave. Please get some stools from there. You can't stand so long. So, sound wave is also interfering. How will it interfere? Have you done Meldis experiment? A vibrating bar. Some of you must have done. So a bar is vibrating. It is producing wave. You have a thread along that, and you are putting it on the what you call a pulley and apply some weights. Is it not? And switch on. You will have the vibrations. And once it is vibrating, you will have the waves that are there. For all suitable distances, it will not produce reflections. Only for most suitable distance, weight, most suitable vibration frequency, you will have reflections. So that reflection, if it is there, going wave and reflected wave, transmitted wave and reflected wave, both are at the same place on the same thread, and you will have, what wave is that called? Standing or stationary wave. So a wave that is there without moving is called a stationary wave. So that stationary wave has got very clear amount of positions. 2 points where you don't have vibrations at all, they are called nodes. Node means the amount of energy there is 0. In middle of these two nodes, you will have energy increasing to maximum and energy decreasing to a minimum. So like that, you will have in the middle, you have an antinode. So you will have in standing waves, nodes and antinodes. Okay. So in the same way, you can also observe the reflection in a particular jar in which you put some water. So keep the tuning fork on the opening of that jar, go on adjusting the water level. What will happen? The amount of air available above the water level within the jar, you will find the air volume is resonating with the frequency of the tuning fork. So like that, you can adjust the volume of the water and get the volume of air. The resonance is not between water and the tuning fork. It is between the air and the tuning fork. So you find volume of sound increasing to a maximum. If you reduce the volume, water still further, volume of sound is decreasing. Like that, volume increasing to a maximum and decreasing to a minimum also is observed in that. Wherever you have that maximum volume, you will find that as resonance. Can you tell me what is resonance?
Opposition, sir.
What is resonance?
Post vibration of one object on effect on another object.
It is an effect of superposition. Superposition of one wave, that is, let us think that it is a tuning fork. A tuning fork is vibrating. It is vibrating with fixed frequency. Air volume within the bottle is a variable frequency. Are you following? Air volume within the bottle is equivalent to variable frequency. If one of the frequencies of that variable frequency of the volume of the air in the bottle is exactly matching with the frequency of the tuning fork, then you will find a booming sound. Okay. So that is the position of what is called resonance. Resonance is increasing the volume of that. In places like wherever you have gold gumbas like things, in some mosques or say some other very big halls, at one end, if you go slowly, call it as boom, then you will have a reflection. And you increase and decrease frequency, you will also have the resonance. So like that, we have reflection of the sound wave, resonance of the sound wave, and refraction of the sound wave, interference. So in light, you have interference. You must have studied that probably in your intermediate also. In this course, probably in second year, you will have the association with light. Light wave interferes, sound wave also interferes. So sound wave interference we have seen, and light wave interference has produced two types of interferences. One is constructive interference, another is destructive interference. So what is constructive interference? Imagine one wave like this. Imagine a second wave exactly like this. Amplitudes of the waves increases, added. Amplitude A1, amplitude A2, both are added. It will become 2 times the amplitude if the amplitudes are the same. So amplitudes will become double. Imagine there are many waves, many waves. All the amplitudes are added together. What will happen? Enormous amount of amplitude, resultant amplitude. Can you give me one example of that? Many amplitudes that are added in a constructive way, producing very intense light. Can you give me one? It is laser. All of you are familiar with the word laser? Not familiar? It has become so popular these days. School people also know all these things.
Laser light.
Laser light. In laser light, you will have one amplitude is associated with the atom associated that is moving from higher level to a lower level. It is jumping from higher level to lower level. So what is the level means? Energy level. So energy difference is also energy. That energy is proportional to frequency. So energy related to frequency, what is that called? What is that formula called?
is equal to h nu.
Ah,
Is equal to h t, sir.
what is that formula called?
Max.
Planck's energy formula. Okay. So this is energy of that particular one. And that frequency of that particular atom jumping from that to this. And this is giving you, what is it giving you? Wavelength also. Once it is a frequency, it's a wavelength. So you tune this in such a way that, what is the meaning of tuning? Choose suitable atoms for the laser, and these two energy levels difference will have a wavelength that is seen by our eye. Are you following? Then you will have the associated light, associated laser light. You can have this as a red laser if the wavelength is in that particular range or frequency of that particular range, or green laser or blue laser, like that. There are lasers throughout the electromagnetic radiation. X-ray lasers are also there. Ultraviolet lasers are there. Infrared lasers are there. So many lasers. Microwave lasers are there. Anything that is above red, that means wavelength more than red, you will have the energy associated with that light, with that electromagnetic radiation, is weaker in energy. Remember this. This is very important for you. So many people are casting aspersions unnecessarily on the various things. Any wavelength above the red wavelength has got the associated energy weaker than the red light. Suppose that light is harming you, red also must harm you. Red must harm you more. Violet must harm you much more. So, what are those weaker radiations? Infrared, microwave, radio, very long radio. All these things are they harming us? They should not. Compared to visible light, microwave is 10 to the power of 6 times smaller in frequency. Smaller in frequency means smaller in energy. Smaller in energy means its harmful effect will be smaller. So now we say microwave. So for all those, something related to phones. What type of phones? Either smartphone or mobile phone, any of those phones. They're all transmitted by microwaves. Are they harmful? They should not be. 1 million times weaker in energy compared to visible light. If they are harmful, we are all troubled by the sunlight. Are we troubled by that? Over so many lakhs of years, we are all living on earth, enjoying sunlight. It's not harmful. So microwave is not a harmful one. Remember that. You must be able to assess things on your own using the formulas of physics and explain people if they are giving you any misgivings. Okay. Now, interference. We have destructive interference also. Apart from constructive, you have a wave. Another wave is starting in such a way that this is going down instead of going up. This is going up and this is going down. So after some time, it will meet here. And again, this first wave is coming down, second wave going up. That means, what is the phase difference between the two? 180 degrees. You must be able to very clearly and correctly explain the concepts called phase difference and path difference. Okay. So when one thing is going up, another thing is coming down, immediately you must be able to say 180 degrees phase difference or phase difference of pi angle. Okay. So if one wave is starting, another wave is either slightly before that is starting or slightly after that is starting. Then what will be there between these two waves? There is a path difference also. The path difference can be 0 to 2 pi. 0 means exactly overlapping. 2 pi means after this wave completes, that wave is starting. Are you able to follow? So the moment you say a wave, imagine a sine wave for convenience. It need not be a sine wave. It can be any wave. I am speaking to you. This is not at all a sine wave. I wanted to show you this on the oscilloscope, but that experiment failed. If you have a microphone connected to an oscilloscope, you will be able to see your speech. That means how zigzag it will be, complex it is. So you must be able to understand that particular waveform. So if you have a light coming from a tube light and the light coming from another colored light, third colored light, many colored lights are there. So all these things put on one, it will be a very complex waveform. Such complex waveforms are solved by one scientist called Fourier. You have that in your syllabus this year. Fourier, as a scientist, mathematician, he has given that any wave which is periodic, you need not write that, they are all available in your books. Any wave that is periodic and single valued, repetitive, will have its components, infinite components in that. That means the speech that you observe in the oscilloscope, very zigzag one, can be explained using a large number of sine waves. Okay, so large number of sine waves, large number of cosine waves pulled together, you can solve that complexity of the wave. Like that, using that Fourier concept, Fourier equations, Fourier what are called transforms, communication systems engineer will be using to process signals. People are speaking through microphone, through their mobile phones. Then you will be able to get a very complex wave. This complex wave is divided into number of cosine and sine waves, and that will be brought into the solution. So a signal can be processed. So this branch is called signal processing. If you have your friends in electronics and computer science, electronics and communication engineering, they will have some subjects called signal processing and digital signal processing, and all these things are processed using the concepts of, what is that? Fourier methods. They are called Fourier methods. Fourier methods are useful to all types of waveforms, all types of signals. It has unlimited applications. So apart from interference, that means sound also has interference. Light also has interference. So you will have light, another property called diffraction. Have you heard of diffraction? In interference experiments, you find one wave is going up, another is going down. At this part, it is nullified. Energy is 0. Okay. And at this part, wherever you have no light, that means wherever you have darkness, you can assume that they are having a phase difference of pi or 180 degrees. That means if you find a darkness at some place, interference is in such a way that, of course, this is in interference experiments. Interference is in such a way that you will find this darkness because of the destructive interference. And if you have brightness immediately after darkness, this is because of the constructive interference. In the same way, in sound also, you will have what is called interference. That means a superposition of waves will produce interference. You will have at some places no sound audible. At some other places, you will have sound. Some other places, very high amount of sound. Can you tell me this phenomenon? This is there in your book. This phenomenon is called beats. Okay. So earlier, the communication between one tribe in one hill village, another tribe in another hill village, is through making those beats, sending the information from one place to other place. Something is very important, they will send this. Human voice volume is not sufficient to go to that part. But if you produce beats, that will go much beyond the limit of this. So, without knowing what is a wave and what is all not, they know how to transmit. So, we will have beats as an example where you have sound interferes in such a way that it is also a modulated one. Have you heard of modulation? What is modulation?
Added some frequency to transmit for long distance. Addition of some additional frequency to transmit a signal to long distance.
How?
Like sir,
frequency modulation. Frequency modulation.
Any modulation.
Some frequency like
some signal can be carried by electromagnetic waves by oscillation.
You are unnecessarily digressing. We require two things. All of you, please listen carefully. We require two things. One thing is carrier wave. Another one is speech wave or signal wave. A carrier wave is the one which carries the signal. Okay. For example, in radio transmission, earlier Hyderabad A carrier wave used to be 404 kilohertz. That is the carrier wave. At that carrier wave, you impose a signal that is called either song or say speech or whatever it is onto that. So the carrier wave will take the signal along with that and go to all places. But there is a limitation. What is the limitation? The height of the antenna is the limitation. If the height is very high, you can increase the area of transmission very big. So now people found that satellite communication has become easy. Then immediately along with that, in earlier one, what I was describing, Hyderabad A, that carrier and signal, that was another type of modulation called amplitude modulation. So immediately after that, frequency modulation has been invented, and using the technology frequency modulation, you can send the signal with more clarity. And frequency modulation is done using the satellite technology also. Nowadays, what you are having a dish over your house is catching the signal is only by frequency modulated wave. Okay. The sound is so clear and you will enjoy the sound. But in TV is the picture. Picture also is a wave, is it not? What type of modulation is it? It is amplitude modulation. Sound is frequency modulation. These are all properties of waves. So you have what is called diffraction also for the property of a wave. A wave can have interference property. It can have diffraction property. You have heard of diffraction? Anybody answers? What is diffraction? Diffraction has been broadly defined as bending of light around an obstacle. If this is an obstacle, a light bends around the obstacle. Have you ever verified diffraction?
Water में अगर हम लाइट डालेंगे तो waves change हो जाएंगे.
I will give you an immediate example. All of you use your 2 fingers. Make a thin slit, thin opening. Try to see through this particular light. Come on. All of you see. Through this thin opening, see the light. Make a thin opening, not very wide, thin opening. What are you finding?
It's a bending, light is bending on the
Don't say that light is bending. You can't see that bending of light.
No. I mean,
see, we only know the effects of that. So what I want is, what is the effect that you have seen?
इसके सामने वो हम लाइट नहीं देख पा रहे, but sand में लाइट देख पा रहे.
When you see through this thin opening, you will find thin lines, thin vertical lines. Come on, see. Thin vertical lines. Don't call whatever word you like. Are you finding thin lines? Thin dark lines? You can see even through the window, that light also you can see. Have you seen that? This is because of diffraction. You should not say this is diffraction. This is because of diffraction.
Splitting of light is.
See, diffraction has got some effects. The effect of diffraction is to produce darkness as well as brightness. This is a crude experiment in which you can see the vertical lines. Why are they vertical lines only? Because you are keeping it like that. If I keep like that, they will be horizontal lines. If you keep a circular one, very small one, you will find a circular contour. Particularly when you have a sodium light kept and go on observing through that, excellently you will get it. Now, with this knowledge, if you concentrate on edge of your finger with the help of light, you will find a layer. Come on, go on, see. Thin layer. Are you finding a layer? So it should not happen, is it not? But it is happening. This is because of diffraction. So it is diffraction effect. So what do you want for diffraction to occur? A source, an obstacle. This is obstacle. or any such things are obstacles. And one observer. Source, obstacle, and observer. So you make suitable arrangements of opening the eye or closing it very narrowly, make such simple arrangements, adjustments, you will be able to see diffraction. And if you are in sunlight, try to close your eye and carefully observe your eyelid lashes. Lashes are there, no? Small hairs. If they have certain amount of oil on that, sunlight falls, you closely observe, don't see the sun, observe the hair. You will find if it is having a thin coating of oil, you find small colored circles. Have you ever observed earlier? In future, you try like this. But never try to see sun directly. That's a very dangerous thing. It will burn your cornea. So never try to attempt that. Okay, you have so many experiments without any equipment you can do and observe, understand the waves and associated phenomena. So you have diffraction in sound or mechanical waves also. In the same way, you will have diffraction, the interference in mechanical waves also. So you will have, so all the phenomena that you are observing in light are also observed in sound. Is it all the phenomena or any one phenomenon that is different?
We cannot see, sir.
One particular phenomenon that you observe in light cannot be observed in sound. What is that phenomenon? Anybody? Think and tell. It may go wrong, doesn't matter.
Light can transmit visible also, but sound cannot transmit.
Light visible, that's the sound visible.
Not necessary. I told you both these things, whether they are visible or not, effects can be observed.
Light can be transmitted vacuum, but sound cannot be transmitted.
That is, light is transmitted in the material medium also. You cannot say that. One particular phenomenon or property of light, that is polarization. You have studied these things in your school as well as intermediate also. Polarization cannot be observed in sound. It cannot be observed in material media. Okay. That polarization is also a wave phenomenon. Because we have waves and oscillations. We cannot rule out any other thing. Everything is available in this. It's a very vast subject, waves and oscillations. Polarization. What is polarization? We have Polaroids in our lab. In future, you can ask madam to show that. If you have one Polaroid, listen carefully. You see through the Polaroid, go on rotating that Polaroid in all 360 degrees, no change of intensity. Keep one Polaroid fixed, keep another Polaroid in the direction and rotate one of the Polaroids, either this one or this one. Rotate it. At one stage, you will find complete darkness. Are you following? At one angle, you find complete darkness. And you rotate further 180 degrees beyond that particular dark position. Again, you find darkness. So, if you have two polarizers, the light that falls on the polarizer comes out as plane polarized light. This plane polarized light is polarized in one plane only. Polarized in one plane only. The light coming from the tube light or sunlight. How many planes it is there? Infinity planes. Is it not? Around a point, if you construct a sphere, it's called solid angle. The solid angle is 4 pi. Around a point in one plane, if you construct a circle, it is called 2 pi. 2 pi is 180 degrees. Around a point in a three-dimensional way. That is a sphere. What is the angle? 4 pi. Okay. In 4 pi, how many planes will be there? Infinity planes. So out of the infinity planes that are falling on the polarizer, only one plane that is chosen. How will it choose? The Polaroid is made for that plane. So only that plane only is visible. Okay. So this plane polarized light is falling on another Polaroid. Then if the plane of polarization of this polarizer and this polarizer both are parallel to each other, then light is transmitted through this also. What is the meaning of that? If you keep one of them, another of them, and rotate, the light brightest point is when they are parallel to each other. Dark means they are perpendicular to each other. So you will have one bright, one dark, one bright, one dark. So between one bright and one dark, what will you have? Intensity getting reduced from brightness to darkness. And from this to this, intensity is increasing from darkness to brightness. Like that, in one complete rotation of one of the polarizers is observed as two darknesses perpendicular to each other. Darkness is one very clear indication for us. If you have such a darkness, that means these are polarized. If darkness is not at all observed on the entire rotation, then there is no change in intensity. Then can you call it as a polarizer? No. There are some eyeglasses available in shops, optical shops. Okay. You must have heard of polarizing glasses. Have you heard of? There are polarizing glasses. You can test it using another polarizing glass. Keep one fixed, another one rotating. The darkness must be available. Then only they are polarizers. Otherwise, they are not polarizing glasses. Okay. So this is very briefly about effect of polarization. We are all talking of you want to say anything? Somebody is talking. The effect of polarization, the effect of diffraction, the effect of interference, these are all effects. So, effect of that only we will be able to know. You are able to see things, is it not? That means they are visible. Are you able to see any wave? You are able to listen to me. Are you able to see, are you seeing any wave? So there is no wave that is seen either in light or in sound. Whereas if you drop a stone in water, you will be able to see the waves. Or if you tie a thread at one end and hold at the other end, make it to move, you will have wave seen. So sound waves and light waves are not seen at all. Okay, that means
except visible light.
visible light also, are you seeing the wave? That's what I'm asking. You cannot see because our eye has the ability of observing effect of light, effect of various waves. See, scientists in 1800s have done so many experiments. At the end, they concluded that because it is a wave nature, we can call light as a wave. Because it has a wave nature, we can call sound as a wave. So now we have facility to see the sound wave on the oscilloscope. If we have a microphone, hold it, speak, microphone is connected to oscilloscope, you will be able to see the wave. If you stop talking, it will be, there is no wave. And if you repeat one particular syllable, say for example, out of the 7 in the music, sa, same thing you continue. Very carefully, you will have nice wave. So it depends on your ability of producing the single wave. Single wave production is very, very difficult. So when I am speaking, so many waves are mixed up. So many frequencies are mixed up. Similarly, when you are seeing the light around, so many waves are mixed up. At a particular point, how many light waves will be there? You can calculate. Use the formula. What is the formula? Formula is C is equal to, C is the velocity of light. You can use it for the frequency multiplied by wavelength. Is it not? That is the formula we use. Okay. Wavelength, C is called velocity of light. Velocity of light value, you know, 3 into 10 to the power of 8 meters or 10 centimeters, whichever way you can put it in, whichever way. And frequency, we will get number of waves in that. Wavelength lambda. Lambda, you assign some lambda approximately middle of the visible light. Visible light is 4,000 angstrom units, one extreme end. Below that is ultraviolet. Another end is 7,000 angstrom units, red end. Beyond that is infrared. So between 4,000 and 7,000, you have got 5,500 angstrom units. 5,500 multiplied by, what is 1 angstrom unit? Ten to the power of minus 8. Minus 8 centimeters. So 5.5 into 10 to the power of minus 5. I have reduced the 3 digits here, reduce that one. 10 to the power of 5. Okay. Calculate frequency. Take this wavelength that side. That will be on the dividing one. 10 to the power of minus 5 going to numerator. 10 to the power of plus 10 plus 10 to the power of plus 5 will give you 10 to the power of 15. Okay. And you have 3 divided by 5.5. So you will have approximately around 6 if we calculate. What is that 6? 6 into 10 to the power of 14 is a frequency. So many waves will be appearing at a particular instant around a particular point. are you able to observe? How many waves are there? 10 to the power of 14 waves. Out of the 10 to the power of 14 waves, which are in which plane? Can you decide? Just impossible. So we cannot have any control on this. Of course, some very big laboratories, scientists are conducting some experiments that is much beyond our understanding. We leave that. Normally, what you can say, we have no control on the number of waves and their phases. Phase of one and phase of another one, phase of third one, they're all different. So what is the net amount of phase? Very low. Very low means it is just whatever that we are accommodated. We are habituated to see that light. But if all the phases of all the light beams are superposed on each other, what will happen? Amplitude increases enormously. What is the example in the beginning I told? That's why if you have a laser beam, very careful, don't allow laser beam to fall on your eye. It will get damaged. But the same laser, not exactly visible, but infrared laser with suitably adjusted power or suitably adjusted that intensity. An eye surgeon can use it to do the ophthalmic operations. But for other operations inside the body, your other laser, visible laser, is very comfortable. A catheter is put and they will be able to see what is inside without harming the body, without doing any operation, cutting, no trouble. And that will be, these days the catheters are becoming thinner and thinner, even without damaging the throat part also. So like that, what all we invented in our waves and oscillations part by our forefathers of earlier scientists are being utilized by technologies. A laser is invented in 1962. Very soon, it became popular in medical region and it became popular in number of wars also. It has its not only industrial applications, medical applications, defense applications. Many defense applications are also there using lasers. So like that, an invention, something like, for example, whatever sound that you don't hear, you call it as, what is the name of the sound? Ultrasonics. Here, what are ultrasonics? What are not ultrasonics? You must know. The sound frequencies usually audible to human being are minimum is 20 hertz, maximum is 20 kilohertz, 20,000 hertz. So above 20 kilohertz, you have ultrasonics. Below 20 hertz, there is a name called infrasonic. Okay. Our interest is more in ultrasonics. Why? You have ultrasonics very conveniently used by a crystal called quartz crystal. In the quartz is hexagonal and you have 6 hexagonal, 6-faced crystal and cut that perpendicular and you prepare a slice in one direction called X direction. It's called X cut plate. If you do it in the Y direction, it is called a Y cut plate. Each has got its advantages. So you have X-cut plate of suitable thickness will have certain amount of frequency. What is this crystal called? Quartz, of course. What is its nature? Piezoelectric crystal. What is the meaning of piezo? If you apply stress, it produces. Piezo means pressure. If you apply stress, it produces electricity. On one side positive, on the other side negative. It can also understand the reverse way. If you apply positive negative signal, it will produce mechanical waves. Are you following? By pressure, you can produce electricity. By applying electricity, you can produce pressure. So like that, you have what are called transducer. You have heard of it? A transducer using either quartz or similar ones. There are many transducers that is connected to a circuitry and ultimately to a screen like our oscilloscope. So what do you observe? You keep the ultrasound. This is called scanning. Ultrasound scanner, I think all of you must have seen. So the ultrasound scanning is very convenient and safe to use medically. X-ray picture, if you take, X-ray is a high energy radiation. It will naturally damage or kill some of the living cells. But when it is necessary, X-ray has to be taken. But for all safer purposes, for example, a lady is pregnant, how the baby is growing, with good health or not, any defects, any troubles. So all that can be seen using ultrasound scanning. So this scanning is done by the quartz crystal, and the frequencies are generally varying from 100 kilohertz above up to 1 megahertz. Sometimes it is 10 megahertz. Whatever is the frequency, it is not a harmful radiation. This is an important thing. Whereas X-ray frequencies are harmful. Are you following? That's why ultrasonics also waves, but they have very, very high frequency. High frequency means wavelength is very low. So ultrasonics using that probes, what are they called as probes, transducers, can also be used for non-destructive testing. In the metallurgy production, and there will be inspection, how the metals or alloys are coming out for very important applications. So they put the transducer and they get the wave transmitted into the material and getting reflected back. That can be seen. Transmitted one and reflected one must have suitable amplitude. If the transmitted one is having higher amplitude, the reflected one is having very low amplitude, there is absorption. So when there is a lot of absorption, that means there is some void. There are some cracks. So like that, in all the things, these days, even railways is using ultrasound railway, that rails, all along the rails, so that they can be, if defective ones can be removed and keep another new one, like that for such things. Otherwise, damages will be very heavy. So like that, ultrasonic are also used for industrial applications. Not only medical applications, they are also industrial applications. So these are all part of our waves and oscillations phenomena. Thank you for listening to me patiently.
Vote of thanks. Thank you, sir, to give our nice lecture. First of all, we will thank to our Dean Madam, HOD Madam, right, to arrange this nice and good lecture. Sir, our students are very benefited, sir. And first of all, I would like to thank you, sir, to accepting our invitation to give nice lecture, and we are very, very benefited. Thank you very much, sir. Thank you, one and all. And also thanks our staff members who have helped to us to conduct this lecture. Thank you. Thank you, one and all. Thank you, sir.
You can see this wave. This is able to send three types of waves. One is sine wave, another is square wave, another is triangular. In fact, there